How can the unit circle be used to define trig functions? First off, what is a unit circle? A unit circle is a circle with radius of 1 centered at the origin. With point P on the unit circle and theta, the angle between the positive x-axis and the line from the origin to point P, sine is the y-coordinate of point P, and cosine is the x-coordinate of point P. For the line from the origin to point P1 to make an angle of 0 degrees with the positive x-axis, P1 must be on the positive x-axis. Since P1 is both on the unit circle and the positive x-axis, its coordinates must be 1, 0, making sine of 0 degrees equal to 0 and cosine of 0 degrees equal to 1. Now with our theta equal to 30 degrees, and our knowledge that an equilateral triangle has 3 angles of 60 degrees each, we can construct an equilateral triangle by first constructing a segment of negative 30 degrees from the positive x-axis. Connect the 2 points in the unit circle and start labeling things. The negative in front of the bottom 30 degrees solely represents the direction that the red line is going from the positive x-axis. So from line OP2 to the positive x-axis we have 30 degrees, and from the positive x-axis to the next red line we have another 30 degrees, giving us a central angle of 60 degrees. Since the 2 lines going from the origin to the unit circle are the radii, they both have length of 1. We have an isosceles triangle, and since it's an isosceles triangle, its base angles must be congruent. Remember, the interior angles of a triangle add up to 180 degrees. So each base angle must equal 180 minus 60 divided by 2, giving us all 3 angles to be 60 degrees. Now that we have each angle equal to 60 degrees, we know we have successfully constructed an equilateral triangle, and so each side must be congruent as well, making the chord of length 1. Because the sides of the triangle were produced by segments from the origin to the unit circle that are 30 degrees and negative 30 degrees from the positive x-axis, we know that the x-axis bisects the chord, making sine of 30 degrees equal to 1/2. Now let's review the distance formula. The distance from point x1, y1 to point x2, y2 is the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Since we'll only be working with lines from the origin to the unit circle, we can simplify this distance formula to the square root of the x-coordinate of p squared plus the y-coordinate of p squared, which is equal to the square root of cosine squared plus sine squared. To find cosine 30 degrees, we will use the distance formula, already knowing the distance from the origin to point P2 is 1, which is the radius, and also knowing that the sine of 30 degrees is equal to 1/2. Then we get 1 equals the square root of cosine squared of 30 degrees plus 1/2 squared. After taking the square root of both sides, we get positive or negative cosine of 30 degrees equals positive or negative square root of 3 divided by 2. Since cosine of 30 degrees is the x-coordinate of a point in the first quadrant, its value must be positive. Therefore, cosine of 30 degrees equals square root of 3 divided by 2. Segment OP3 makes a 45-degree angle with the positive x-axis. Let's make a perpendicular line to the x-axis to point P3. Now we have a right triangle. Since the interior angles of a triangle add up to 180 degrees, then the third angle is 180 minus 90 minus 45, giving us another angle of 45 degrees. Once again, we have an isosceles triangle. We know we have an isosceles triangle because we have two congruent base angles. Since this makes the two sides also congruent, we have cosine of 45 degrees equals sine of 45 degrees, which implies cosine squared of 45 degrees is going to equal sine squared of 45 degrees. By the Pythagorean theorem, c squared equals a squared plus b squared, where c is the hypotenuse of a right triangle and a and b are the sides, we get 1 squared equals cosine squared of 45 degrees plus sine squared of 45 degrees. Since cosine squared of 45 degrees equals sine squared of 45 degrees, we have 1 squared equals 2 times sine squared of 45 degrees, giving us plus or minus square root of 2 divided by 2 equals plus or minus sine 45 degrees. We know sine of 45 degrees must have a positive value because it is the y-coordinate for a point in the first quadrant. So sine of 45 degrees equals square root of 2 divided by 2, and cosine of 45 degrees equals square root of 2 divided by 2. Segment OP4 makes a 60-degree angle with the positive x-axis. Make a line from point P4 perpendicular to the x-axis. Since the interior angles of a triangle add up to 180, then the third angle is 30. We got this from 180 minus 90 minus 60. Recall the law of sines. It states that sine of angle A divided by the length of the line opposite of angle A equals the sine of angle B divided by the length of the line opposite of angle B. In this case, the law of sines is going to give us sine of 60 degrees divided by 60 degrees equals sine of 30 degrees divided by cosine of 60 degrees. This implies that 1 equals sine of 30 degrees divided by cosine of 60 degrees. We already calculated sine of 30 degrees to be 1/2, meaning 1 equals 1/2 divided by cosine of 60 degrees. This gives us that cosine of 60 degrees equals 1/2. To find sine of 60 degrees, we will use the Pythagorean theorem. This gives us 1 squared equals cosine squared of 60 degrees equals sine squared of 60 degrees equals 1/2 squared plus sine squared of 60 degrees. This gives us that plus or minus square root of 3 divided by 2 is equal to plus or minus sine of 60 degrees. Since sine of 60 degrees is the y-coordinate of point P4, which is in the first quadrant, then sine of 60 degrees must be positive. Therefore, sine of 60 degrees equals square root of 3 divided by 2. At 90 degrees from the x-axis, point P5 lies on the unit circle and the y-axis. Therefore, the y-coordinate of P5 is 1, and the x-coordinate is 0. So sine of 90 degrees equals 1, and cosine of 90 degrees equals 0. By mirroring these segments about the x-axis, we can see how the same methods can be used to obtain values for each sine of 180 degrees minus theta and cosine of 180 degrees minus theta, giving us the same values for sine of 180 degrees minus theta as sine of theta, and the same values for cosine of 180 degrees minus theta as negative cosine of theta. Let's pick one of the new points and calculate its sine and cosine, just in case you're having a hard time seeing how this formula would hold true. Let's look at point P8. Segment OP8 makes a 150-degree angle with a positive x-axis. Before we begin, note that 150 degrees equals 180 degrees minus 30 degrees. Like we did with OP2, which